In this video, we're looking at polar form for complex numbers. So we're used to writing a complex number like this. It goes on an axis. It has a real coordinate of a and an imaginary coordinate of b, and we write it as a plus bi. That's definitely one way to describe where it is. But we can describe where it is completely using its modulus and its argument. So if we call its modulus r and its argument theta, well, you could describe it by saying how far away are you and what angle are you going. Let's see if we can work out these coordinates. Well, the coordinates at that point is going to be, well, if we think about our unit circle, sort of the x coordinate is cos of theta and the y coordinate is usually sine of theta. That's if the unit circle has a radius of 1. If it has just any old radius, you have to times by the radius as well. So those are the coordinates of that point. Now, we don't write imaginary numbers as coordinates. We write them like this, r cos theta plus I times r sine theta. Or if you like, probably r sine theta times I is the nicer way to write that. So what we can do is we can call this SACE theta. So a condensed way to write cos theta plus I sine theta is SACE theta. So if you pull out r as a common factor first, you're left as cos theta plus I sine theta. And this whole thing in here is what we call SACE of theta. So r SACE of theta. The C stands for cos, the I stands for I, and the S stands for sine. So that's another way to write complex numbers. So let's do a few examples. We're converting z equals 3 plus 4i into polar form. Now, if you're comfortable with modulus and argument, you're going to find this really easy. If you're not, you're going to find it really hard. So if you do struggle on this, I would recommend you go back and revise modulus and argument, which would have been the last topic. So this becomes root 25, which is 5 for the modulus. Argument of z, because 3 plus 4i is up here in the top right quadrant, it's the easier one to calculate. You do inverse tan of b over a, which is inverse tan of 4 over 3. And if we work out what that is, that'll give us the argument. (0.927) radians. Make sure your calculator's in radians before you do any of this. So I can write z as 5 cis of 0.927. Now I really want to explain why this is actually equivalent. So the question's done at this point, but what I mean is 5 cos of 0.927 plus I sine of 0.927. That's sort of the full version. And if I convert this back, maybe let's just do the real bit for an example. If I do 5 times cos of that number, I should actually get 3, which is my real bit, and I do. And if I do 5 times sine of that number, I should actually get about 4, which I pretty much do. The only reason I don't is because I rounded it off a bit. So that's cool. All right, next thing we do is convert back to Cartesian form, which is exactly how we did before. So w equals 2 cos of pi over 3 plus I sine of pi over 3. So this is going to be, well, let's figure out what cos of pi over 3 and sine of pi over 3 actually are. This is where you'll pull up like a trig table or something. Pi over 3, so the cos is a half and the sine is root 3 over 2. 2 times a half plus I root 3 over 2. So 2 times a half is 1 plus root 3i. There we go. That's Cartesian form. All right, next thing we do is we times cis's together. Now, normally if you're timesing a complex number, if you think about it like 1 plus 3i times 2 take 4i or something, you'd have to FOIL it out and it's going to be really messy and we just get very sad. So the good thing about polar form is it's really, really easy to times numbers together. All you do is you times the modulus and you add the argument. That's literally all you do. So z times w equals, I guess 3 times 4 would be the argument, because 3 and 4. Sorry, 3 times 4 would be the modulus. And cis of pi over 4 plus pi over 3. Just like that. Times the modulus, you get 12. Add the argument, well, maybe I could write these both over 12. So that's 3 pi over 12 plus 4 pi over 12. So if I add those together, I get 12 cis of 7 pi over 12. Now, actually what people struggle on most with this topic is the fractions. So with the fractions, what you can do, we're trying to do pi over 4 plus pi over 3. You can just do 1 over 4 plus 1 over 3 and convert that back to a fraction, and that gives you 7 over 12. So your calculator can help you with this step to skip it. Use that if you're getting stuck. On a Casio, to be similar, you just use that S arrow D button to swap between. All right, dividing is pretty much the same. So instead of timesing the modulus and adding the argument, you divide the modulus and you take the argument. So z over w equals 12 over 6 cis of pi, take pi over 4. So that's 2 cis of 3 pi over 4. Because imagine if I've got a whole pi and I take a quarter, I've got 3 quarters left. Great.